General relativity, step by step. I've been considering geodesic motion in the vicinity of a black hole, and I've got these four beautiful equations here that I've been talking about, and now I'm going to see if I can come up with some solutions for them. They're quite complicated in their full generality, but we'll make some simplifications, and hopefully we can get some physical insight. The first one I'm going to do is I'm going to assume that theta equals pi by 2. And that straight away, this equation straight away tells me that theta dot equals theta dot dot equals 0 is a solution, because cos of pi by 2 equals 0. And from this equation here, I'm going to further... so that means that I can consider equatorial motion. And I'm further going to consider phi equals constant as well. So I'm just going to ignore that. I'll relax that assumption later on. So I'm just going to consider equatorial motion, and phi equals constant is evidently a solution because phi dot equals 0. Well, this constant equals 0 will do as a starting point. So I've basically got these 2 points here, and I'm just going to rephrase them in a slightly different way. I think I had a sign wrong here. It's very easy to make this kind of mistake. So we've got t by d tau times 1 minus 1 over r equals k. That's a constant. Motion, that's an energy equation. And we've got this equation here. And of course we know what the Schwarzschild geometry is, so I can just expand that. And we can use the nice feature of the Schwarzschild geometry that the metric tensor is diagonal to help us in our calculations. So I'll just write down the line element squared, which equals minus 1 minus r dt squared plus dr squared over the same thing, plus the other terms which are, by this argument here, going to be set equal to 0. So what does this equation give us? So we know what the fundamental tensor is here. We've got two non-zero terms on the diagonal, one here and one here. So what does that tell us? That tells us that minus 1 minus 1 over r times the first element dt by d tau squared, because it's x dot alpha x dot beta, and alpha equals beta equals 0, plus dr by d tau squared over 1 over 1 minus 1 over 1 minus 1 over r equals minus 1, and that's our other equation there. Now, of course, what I'm going to do is to use this equation here to give me an expression for dt by d tau squared, which equals k over 1 minus r. Sorry, that should be all squared. And so I can just substitute in this equation here. So that gives me that minus 1 minus 1 over r times k squared over 1 minus r all squared, plus dr by d tau squared over 1 minus r equals minus 1. I think I had a sign error. Yeah, that should be a minus 1. It's easy to get these signs incorrect because different people use different signatures on the metric. So I'm trying to be consistent here, but it's quite a hard job to do. Okay, so what does that tell us? That tells us that minus k squared 1 over 1 minus r plus dr by d tau squared over 1 over 1 minus r equals minus 1. And that tells me that dr by d tau squared equals minus 1 minus 1 over r. From here, that's a minus, so that's a plus k squared. And I've multiplied by 1 over 1 minus r. So long as r is not equal to 1, we're okay here. Now, there's different ways to write this, but I prefer to write it like this. d tau squared equals k squared minus 1 over r. Always assuming that 2gm over c squared equals 1. So I guess I could write that down as k squared minus 1 minus 2gm over c squared over r if I really wanted, but it's just a pain in the neck. Just set it equal to 1. Get rid of that. So straight away I know that k squared minus 1 over r has got to be greater than or equal to 0 because it's the square of something. So that tells me that k squared has got to be greater than or equal to 1 over r, 1 minus, it's easy to get these signs wrong, 1 minus 1 over r. So example, if r equals 2, if you're at 2 Schwarzschild radii, then that tells me that k squared is greater than or equal to 1 minus a half equals a half, and so we've got a restriction on k. Observe further that if r is less than 1, there's no restriction here. So this inequality here only bites, it's only an active constraint if you are outside the Schwarzschild radius. Yeah. Whew. Right, I'm going to stop there because I think we've got quite a nice little result here. We've got an energetic constraint, and I'll show you what it means in the next screencast, but I'm going to stop here simply because I don't want this one to get too long. Yes, and what I'm going to do, now that I've got my expression for dr by dt, I'm going to substitute that in the next screencast into this equation here. No, I won't. I'm not sure what I'm going to do next. I'm going to stop. Anyway, stop.